Hey folks, this video is on work and power, topics that are presented in somewhat an isolated fashion compared to energy, and so the next video after this is going to bring it all together, hopefully. So work and power related to energy, but in ways that you will maybe see here. This idea of work is specific to science. So, I have a job and I teach and I do a lot of work at my job, but it is not the same thing as work from the science perspective. Work is the amount of energy transferred by a force. So work represents the transfer of energy. And by transfer, I mean moving it from one place to another or from one object to another. So the energy definition, energy is the ability to do work. This is the work it was referencing. And work represents the amount of energy transferred by a force. The equation for work, work is a capital W. And we have a new type of situation here. Work is equal to force times displacement, but it is the component of the force that is parallel to the displacement. And so if you want to write that down, that's probably a good idea. Work is equal to the amount of force that is parallel to the displacement times the displacement itself. This particular notation is F parallel. Force and displacement are both vector quantities, and we have not multiplied vector quantities together yet, and so now we're going to do that. When you multiply two vectors together, there are two ways to multiply them together. There's a way to multiply them so that you get a scalar quantity, and there's a way that multiplies them together to get a vector quantity. What we are going to do is the scalar product. If you take more math and more physics in college, you will learn more about this sort of multiplication of vectors. The scalar product is also referred to as the dot product. So, a physics student in college or a professor might say that work is F dot D. And so now, if you've never heard these phrases before, you're realizing maybe now that there's two symbols for multiplication that you might have used in all of your math classes leading up to this, a cross and a dot, and they actually mean different things when you're dealing with vectors, even though you would kind of use them interchangeably. Anyway, the way that we deal with a dot product in an algebraic physics class is to say, well, we can just multiply the force by the displacement and put in cosine theta, where theta is the angle between the force and the displacement. Okay, so that's, I'll show you some examples of this, but that's kind of the main idea, is that if we put in this cosine theta, we actually are calculating the amount of force that's parallel to the displacement. The units are Newton meters, because it's newtons times meters, that's obvious, which means that if we take the Newton and break it down, a Newton is a kilogram meter per second squared. If we multiply that by meters, we get kilogram meters squared over second squared, and the unit is the joule once again. So the units of work are the joule, which should make sense. If work is defined in terms of energy, then it should have the same units as energy. So for our first example, we're going to talk about like pulling a sled. And so, maybe you did this recently. Here's the sled. And here's the rope that you're using to pull it. Make yourself tall enough. Okay, there we go. And so you're pulling that sled like that. From the point of view of the sled, the free body diagram is going to have gravity, it's going to have the normal force, and it's going to have this force of tension here. Okay, sure, there's always friction. Okay, so that tension force is at an angle. And so if you pull the sled, then you're going to pull the sled at an angle, but when you pull it, it's going to run right along the snow. So if I think about this in terms of a diagram, I would say that the force of tension is in this direction, And the displacement, now this is no longer a free body diagram. The displacement is going to be right along the surface of the snow. And those two things have an angle between them. And so this is where the FD cosine theta comes from. I take the force, multiply it by the displacement, and multiply it by the cosine of the angle. The only thing I want to show you is this. If I take, if I treat this tension force as, you know, a right triangle, the way that we've done it kind of all along since we've talked about trig. Well, I have tension is the hypotenuse of the triangle. There's the theta. This is the x component of that force. This component is equal to ft cosine theta. So all that I'm doing when I do fd cosine theta is I am actually finding the component of the whatever force that is in the same direction as the displacement. And so that little arrow there is ft cosine theta. It's just a little trick of the properties of multiplication that you can like rearrange f cosine theta to be fd cosine theta. So kind of like ft cosine theta times d. Okay, so that's the work equation. We'll go into some examples in another video, but there's one more topic about work that is of importance to us because we do talk about variable forces in this unit and this course. So work is also defined as being equal to the area under a force versus displacement graph. And that is more just like a fact for you to store away for later that we will use a few times. So, you know, work can be done by any force, which means that work can be positive or negative. So if I have a force versus position graph and I have, you know, situations where this is happening. Okay, so maybe that's my force versus position graph. My area under the graph is going to be, well, this was positive work. This was negative work. This was positive work. If I add up the areas of those three, I will get the work done. And so the reason I drew this graph is because I just used the phrase negative work. I wanted to make sure that I used that phrase. So for our final example for work, instead of pulling a sled, I want you to imagine that you're like chasing after a shopping cart. And so now I'm going to attempt, I've set it, I'm going to now attempt to draw a shopping cart one-handed. Okay, so there's like the bar, and there's the wheel, and then there's the bottom of the cart, there's the wheel. It looks kind of like a shopping cart. It looks a little bit more like a wagon. And so what's happening in this situation is you want to imagine yourself in the parking lot of a grocery store, and you have let go of your shopping cart, and it has started to drift away. And you run after it, and the thing that you do is you pull backwards on it. So you apply a force away from the direction that it's moving. And so if we like think about this in terms of work, here's our shopping cart. Its displacement is going to be in this direction. Now it's going to be a small displacement because you can probably stop it in a very short amount of time. But you are going to be pulling very hard with an applied force in that direction. So what does that mean? Well, from the strict standpoint of the equation, the angle between the force and the displacement is that. So in this situation, we would say that you are doing negative work on the shopping cart. Okay, so work can be positive, work can be negative. And so, you know, if you want to think about it in terms of like a force diagram, well, this force only has a negative component. By doing FD cosine theta, you are actually finding the component of the force that points in the opposite direction as the displacement. So, as our finale for the work equation, if you wanted to summarize this situation, you have positive work when theta is between 0 and 90 degrees. You have negative work when theta is between, not equal to, when theta is between 90 and 180 degrees. And then you have 0 work when theta equals 90 degrees. And it's very easy to prove this mathematically. If you just break out your calculator, hopefully mine shows up pretty well on here. And we do some cosines. We do cosine of like 45 degrees. That's a positive number. Cosine of 89 degrees. That's a very small positive number. Cosine of 90 degrees is 0. The significance of this in physics is that it's saying there is no component of the force that is parallel to the displacement. It's a right angle, and so it's not actually affecting the displacement of the object. If I go above 90 degrees, all of a sudden I have a negative number. So cosine of 179 is very close to the maximum negative number. So depending on the angle between force and displacement, you can do positive, negative, or 0 work on something. Okay. So we'll do a lot more with work, but that's kind of your basic intro. And then the last thing is power. And so power is the only situation in this unit where we introduce time. So power is the rate at which work is done. Its alternative definition is the rate of energy transfer. And this will kind of serve as a bridge. If you think about like a car's engine, its job is energy transfer. It takes the chemical energy of the gasoline and converts it into the mechanical energy of the car. Power, capital P, it's the rate at which work is done. So it is equal to work divided by time. So that's great. Work per time is power. And also, the same token, it's the rate of energy transfer. So it's the rate at which energy changes divided by the time. So those are both the definition of power. The only thing I wanted to show you is if we take work, if work is FD cosine theta, then power equals FD cosine theta over time. This is a little significant because in this equation we have distance divided by time. And so I can simplify and I can say that power is equal to force times speed times cosine theta. Sorry, force times velocity times cosine theta. So these two equations are in your equation sheet. So is the work equation. This one is not because it's derived from those equations. The kind of footnote to all of this is when you are dealing with work per time or energy per time, you are dealing with the average power only, because it does not talk about how anything gets from place to place, just that it goes a certain displacement. So this displacement is not attached to a specific velocity, and so it's just how much displacement has it covered divided by how much time. This, however, the P equals FV cosine theta, can be average or instantaneous. And just one thing to maybe think about is that the power there is a power associated with a falling object. And so if an object is accelerating, then its power is actually constantly changing because presumably the force is constant, but the velocity is not. So for something like like an engine, the power output is very constant as long as the car is doing a consistent thing. But for something that's falling or accelerating, then the power is actually changing because the speed is changing. So that's a brief introduction. Well, not that brief, but an introduction to work and power.